For those who don't understand what this expectation maximization does, we have another slide here. Okay, so we are done with all the equations and everything. Okay, and this one is additional explanation. So since zeta is unknown, we want to maximize the expectation of log probability or joint probability or likelihood across all possible z. So if we use the best z, okay, this one is a z. Even though this one is just one-dimensional, it could be, high-dimensional vector. And in this dimension, we can choose the best z, okay? If this one is our best z, then we have this probability here, this green one. Then to maximize this green one, the theta would be around here. And that might be slightly different from m steps parameter in EM algorithm. Okay, if we use the best z, then we pick one distribution and we maximize the distribution with this parameter. Okay, but in EM algorithm, instead of using just one z, we actually use expectation of all of them. So this one in this graph, it says we have lots of distributions like this, and then this one, the purple one, is actually the expectation of all these distributions. Okay, and we want to maximize these expectations with respect to theta. Okay, so our estimate is here, and this one is maximizing this purple one, which is expectation of all these distributions. Okay, if we pick the best z, okay, then let's say best z is here, then if we maximize this one, then the best theta would be around here. So that's the difference between the EM algorithm and other alternative optimizations. Okay, now let's go back to mix of Gaussian. So mix of Gaussian can be trained with EM algorithms. Okay, and in each step, we have to get the probability of this assignment. Okay, not just a single assignment, the distribution of assignment. Okay, so given this point x sub n, then what is the probability of this one? What is the probability that this xn belongs to the ith component? Okay, so that is actually responsibility. Responsibility means one component is explaining this sample this much. Again, if this one is our distributions, then let's say this one is our sample x, then probably this component explains x more than this component. So this component is more responsible than this one about x. Okay, and this responsibility can be obtained by this one. So look at this one. This one is actually a part of this summation. Okay, and we sum up all this probability, and that is denominator, and this one is numerator. So this one is ith component, weight and likelihood. So given one component I, then weight times likelihood, that is the numerator, and in denominator we actually sum all of them. Okay, so the first component explains this x sub n, and the second component explains the x sub n, etc. And we sum all these probability, and this means how much this component explains x sub n. So this one is actually corresponding to this one, like this. That is E step, and the M step is, So we actually use likelihood here. So we want to maximize this likelihood, and the likelihood can be rewritten in this way because we have a mix of Gaussian and we have lots of samples, and samples are IID, so we can multiply, we can product all these probabilities. Okay, so we have a product here, and then we have a mix of Gaussian here. Okay, this one is our definition of this likelihood. And we introduce a hidden variable z. When we introduce z, it means we assume that z is given, okay, which means we have complete data. So we actually have x and z is hidden, okay, but if we have z, so if we have complete knowledge, then this probability can be rewritten in this way. Okay, so by this complete data, we have x and z, which means if we have x and if we have a z, then we know where it is. Okay, if it belongs to ith cluster, then the probability of this one is this one. Okay, that's simple. Okay, it means if xn belongs to the first cluster, then pi 1, mu 1, sigma 1. So this is the probability if x 100% belongs to the first cluster. Okay, so we can use this product with this power. Okay, so if xn belongs to the ith cluster, then it will be like this. This one will be 1 and the other cluster will have zeros. Then we will have only one probability distribution from one component. Okay, then next we take a log. Okay, then this product will be a sum. Okay, and then z sub and I will go here, and we have log pi and log n. Okay, so now next we take expectations, and look at this one. Expectation of z sub and I is responsibility here. Okay, think about this Bernoulli trial. The expectation of x, when we toss a coin, the expectation of this event is actually probability. And the probability of z sub ni is actually a responsibility here. And log pi and the log Gaussian. Okay, so this is the loss function. Now let's take the derivatives and set them to 0. So this one is our function, and take a derivative with respect to pi sub I, and then set it to 0. Then simply we get this one. Pi sub I is the average of responsibility. So we have n samples. Then for n samples, the ith component has responsibility. Okay, then we sum them up and take an average. If it is k-means, then this responsibility is exclusive. Okay, then we just count how many samples are there in each cluster. Okay, we just count and then divide by the total number of samples. But in this case, it is a soft assignment. Then we have to sum all the responsibility of sample n in cluster I. Okay, then we divide this number by n. That is pi sub I. Okay, and for mu and sigma I, it's basically the same as in the single Gaussian case. Okay, take a derivative and set it to 0, and we will get this one and this one. But look at this one. we introduce a new responsibility term here. So in single Gaussian, so when we use maximum likelihood estimator, mean is actually the average of samples, okay, in the cluster, so n sub I. But in this case, we have a responsibility terms, how much this x belongs to cluster I, right? So we actually in MLA or in k-means algorithms, we used n sub I, and x belongs to cluster I and x, right? So this is the mean and the k-means algorithm. Actually, we used S, I think. But in this case, instead of checking the samples in the cluster, we check all the samples from the first to the last, because this is not a hard decision. So when we have distribution like this, even when the sample is around here, this one belongs to the third cluster somehow, because the third cluster's Gaussian distribution might be like this. Even though it is close to 0, but still there is some probability there. So we have to check all the samples, but with different responsibility. In this case, the third component has not so much responsibility for these samples, so this one might be close to 0, okay? But anyway, we have to check all the samples, but we have to divide this sum with n sub I, okay? And n sub I is actually sum of the responsibilities and of the ith component. Okay, likewise, we can actually get a covariance matrix for the ith cluster. Okay, good. So now we have all the equations for mix of Gaussians. So initialize pi and mu and sigma as we did in k-means algorithms. In k-means algorithm, we don't have this one, we have mu's, and we don't have covariance matrices. And in the E step, we actually calculate responsibility of cluster I for sample n. And in k-means algorithms, we have hard decisions, right, with identical distributions. That's why we don't care this part in the k-means algorithm. So now in M step, we update this mean and the variance and the number of samples. Actually, this is not a hard decision, so we cannot say how many samples are in such cluster, but we can say how much samples are in the cluster roughly based on this one. So n goes from 1 to n. So we check all the responsibility. So yes, n sub I means how much this cluster is responsible for all the samples, right? And we can update covariance matrix, and we can update this prior, the weight. Okay, and then we repeat this step 2 and 3 until it converges. Okay, so with this algorithm, we can find the 3 clusters for these samples. So we have 3 Gaussian distributions like this. And this is an example of EM algorithm for mix of Gaussian for 2 clusters. I got this one from sklearn here. And look at this figure. We start from random initials like this, but gradually it converges to 2 clusters with the beautiful Gaussian distributions. Perfect.